Thank you. This will be a more practical talk in the sense that I'm not going to try to prove anything mathematically, but I want to show you some things you might be able to use if you're building reservoir computers, or you're trying to study them in other contexts besides things that are on the computer. And I'll talk a little more about that. As you could tell, some of the sense of some of the talks, especially from Ed Otts, is that the AI world has influenced nonlinear dynamics, and the idea is to, I think, reverse that to some extent too, and have the nonlinear dynamics community influence the AI world and kind of set some things straight. And I kind of want to do that in a sense of coming in, especially from an experimental angle. Although I don't do experiments, but Tom Carroll, who's my partner at the Naval Research Lab, does. And it's good to be connected to people who do the experiments because it keeps you grounded in a sense. It makes you realize there are issues that you have to deal with beyond the mathematics. So I think most people are pretty familiar with reservoir computing in the audience. I'll just kind of go through this fast. And I'm going to use the same system as for the input or the drive of the reservoir computer, and that'll be a Lorentz trajectory, and I'm going to use that to drive the reservoir computer. I'm sorry, the pointer's not working here, which is in the middle here. And of course, you do the output and then take that output and put it through some weights up there, and you can reproduce the Y and Z components, for example, from a Lorentz trajectory by only driving the reservoir with the X component. And the nice thing about it, as Ed Ott mentioned in his talk, is it's fast training. You only train the output weights, and the reservoir is unchanged, unlike the usual deep learning and so on. So and it's fast operation. Whatever their reservoir is, I know most people think of it as being on a computer, and for the most part it is in terms of research, but people are really talking about building these things, and I'll mention some other aspects where it might come in too. And so you kind of want to think about it from that point of view, and from that point of view it could be fast operation. If these are laser interactions, they can operate very fast, and so the reservoir can just operate at top speed at all times. The nonlinearity? Well, you would expect it to be with the nodes, the green nodes in the reservoir itself, and it could be in the couplings also. So either way. What can a reservoir computer do? I kind of sort of mentioned that already, but something as simple experimentally as a plate of water or a pan of water vibrated can do some analysis of the vibrations from an acoustic input. And that's probably, I was explaining to someone else earlier, that's probably because what you're doing is setting up modes in that water, and those are like the nodes in a reservoir computer in interacting, especially in a liquid where the interactions, where motion is nonlinear, so there are relations. People have also talked about using spintronic devices. In our laboratory, people are talking about using quantum dot lasers. Memristors were mentioned. So you have a lot of different experimental things that people are thinking of using as real reservoir computers, as real devices you can put in drones or remote control aircraft or sea devices, and have them do particular computational work without having to put a computer on board. So all of these have the same idea that you take the output from a particular input and you can recreate, in this case for the Lorentz, the Y and Z components, things that you seemingly didn't put into the reservoir. So you could drive with one signal, and even experimentally, as the point here, and you can reproduce other signals. And I think for me, one of the most interesting things is this might be something that happens in neuronal networks, real neurons. And this came up this summer. I was at a Networks of Physiology conference, and people were very interested in this idea that saying that maybe some of the neurons that are being cited in your brain right now might be doing some reservoir computer type things to help you analyze sensory input. And there are some things about the mathematical aspects of reservoir computers you would want those to have, like something called generalized synchronization. You want them to fall into the same state with the same sensory input. That helps you remember things. So I'm proposing that as a possibility. That's a long way off, but it is something that this could be applied to and maybe explained biologically. There are a lot of other links. So I'd like to give you that because expand your viewpoint away from using computers all the time to do this, although those are interesting and useful ways to do it. But the world around you may have a lot more reservoir computers already being used. So I want to talk about embeddings. The reservoir is, let me back up here. The reservoir is, I've kind of glossed over, is recreating the Y and Z component. You can get the output and you're driving with the X, but you get Y and Z out. So the idea is that the reservoir is probably creating some values of the Y and Z within itself, even though it was only driven by the X component. So what we should do is go back to Tockin's theorem, and I can show you why that's probably happening. And I think Professor Ortega, who just gave a much more in-depth mathematical talk, would probably agree, and some of his stuff is to take you even beyond this. But let's just stick with Tockin's theorem. This was done in 1981, and he says, suppose you have an experiment where you measure only one component of a system, but you would like to get information about the attractor that came from. And usually in experiments, you only measure a few components of things. It's rare you measure all the dynamical components. So the idea of Tockin's approach, he didn't come up with the idea, but people were doing this but didn't know if it was right, but he proved why it works. And that's that you form these delay vectors. So you make a vector out of the output of your measurement in an experiment by just taking the measurement the previous time, 2 times the previous times before that, and so on, and you make a d-dimensional vector. And then you shift them all to make another vector, v2, and you shift them again to make another vector, v3. So that gives you a bunch of points in this pseudo state space. And this seems to, at the time people did this, it seemed to recreate some kind of an attractor, maybe a little bit warped from the original one, but it looked geometrically correct. What Tockin's did is he proved that, in fact, this reconstructed attractor with these experimental vectors is actually a diffeomorphism of the original attractor of the original system, which you can't, all of which you can't see, but you're looking at a good reproduction of it. And diffeomorphism, of course, means it's continuous and indifferentiable, and the inverse, continuous and differentiable. And you need the Whitney embedding theorem to really prove that. Not going to get into that, but this was a big step in 1981. And so the dynamical and geometric properties of the original attractor that you can't see are recreated in a reconstructed attractor. The question of what time delay and dimension to use, that's still being worked out. That's not really been fully nailed down, even though it's been going on for quite a while. But it does work, and there's a theorem behind it. And that's going to be important because I can just show you, this is a simplified version of what Professor Ortega showed. I can show you why that's going to work, why Tockin's theorem comes up. And in fact, he's used it in some of his papers as a stepping stone into the more general theorems he's proven. So if we take a input, let me use a kind of simple iterated map here. And so we have an input from X, a dynamical system X, which by the iterated function H moves to the next time step. And then we take some function of that. We could just take a component of X, for first component or whatever, and we drive a reservoir computer with that. And then we get an output, and the output is functionally related to its iterated function, which has the input from itself and the input from what you're driving it with. So R at t in the next time step is related to the previous time step along with the driving. And if you think about this, then this previous time step, R at t minus 1, can also be written that way. Simplistic, but if you do that, you actually then get a set of iterated compositions of the function F going back in time. That ought to look similar to the Dawkins theorem. And in fact, that's basically what's going on here. So that the output is dependent on those previous times. It's also then, by Dawkins theorem, going to be related to the actual dynamics of the attractor. And you can put some more conditions on that and show that this will converge and so forth. Sorry. A misprint, I'm not sure.
The numbers on the slots seem not very good to work out.
This one?
That's it, yeah.
Might have been. There might be one there.
Some minus and some pluses.
Well, I'm moving it ahead in time. This was a. Oh yeah, these should be minuses. Sorry. Yeah, that's the bottom one. Yeah, they should all shift. It should be a shift. Thank you. It's good to know somebody's paying attention, more than I was. Thank you. Yeah. U is just an input function, and it could just take one component of the x and use the driver. For the Lorenz example, you would have taken just the x and driven the reservoir. So dynamically driven reservoir computers can reconstruct, they are internally reconstructing the attractor of the drive system through Dawkins theorem. So let's take a look at this and ask ourselves, can we determine when that's happening? You're in an experiment and you're in the middle of it, you take some data and you have your reservoir computer, and maybe you can tap off of that and take data from that. And okay, you take a look at the Lorenz system and you take a look at, let's say, a 100-node reservoir computer. And you look at two of the nodes and you can see there's a similarity there. That's, a lot of people have noticed this, that's easy to see. But it's a 100-node system. And the question is, what can you do about this in an experiment? Because you don't have access to all of the variables at sometimes, but even when you do, you may not know the dynamics of the reservoir computer. There's a lot of assumptions in these mathematical theorems, but how would you know that you're really getting a continuous and differentiable mapping of that, of the original drive system? And so what I'm saying is, I'm going to develop some statistics that allow you to address that. So this is for people who are taking data or even doing numerical calculations, and you'd like to see, am I indeed getting an embedding somehow in that reservoir computer? Because in a 100-node computer, looking at two components really doesn't give you the full answer. So we're going to develop statistics that do. So I'm going to develop statistics. Mostly I'm going to concentrate on continuity statistic. You can develop a differentiability statistic, and you can come up with other measures, but I'm going to mostly stick with the continuity statistic. So I'll take the reservoir, so the Lorenz system, and I'm going to take a reservoir computer based on a system that Tom Carroll used when he was looking at these things. He's done a lot of work looking experimentally, numerically experimentally, at some of the things that people assume about reservoir computers, and found out some are right, some are wrong, and some need to be tuned. And I would recommend his papers because there's a lot of information there on really looking a little harder at things like fading memory. What does that mean? So what Tom has is a set of nodes which are, their dynamics individually are polynomials, R1, so R squared, R cubed, and they're linked together with a adjacency matrix or coupling matrix, and there's an input of the X from the Lorenz system with some weights, Wi. So that's the dynamics of the reservoir computer. And now the question is there a one-to-one continuous mapping between those two? And to try to tell us whether there's a chance that we are actually, that reservoir is actually reconstructing the attractor. And so I need a statistic for continuity. This is something we came up with quite a long time ago in a different context. And we've refined it over the years, and after looking at the reservoir computer problem, I realized it would be a nice statistic to pull out because this is a central question in a lot of what you do in reservoir computing. So I'm saying, okay, we have a drive, and let's suppose we have access to all of the parameters for now, just to see whether we can look at, is there a relationship between the drive and the reservoir computer system? So typically, you take the simple Calculus 101 definition of continuity. For every epsilon's a delta, with that whenever things are within delta, the functions are within epsilon. And you can make epsilon smaller and smaller, and there will always be a delta for which this will work. So how do you do this with data? And that's the trickier part. Most people think of that in terms of analysis, but you can do it with data. At least you can make a statistic to do that. That's what I'm going to do. So we're going to basically say, okay, let's look at a set of points on the function range and see if there's a delta that will map into that small set of points. And if it maps into a big set of points, we're going to say, well, that's not much chance there's continuity. So it's like the continuity definition, but in terms of statistics, you keep shrinking that epsilon down and seeing if you can find a delta which will make it work. Now, what does that mean, make it work? Well, if you're mapping points from one of the domain into a range, we need a null hypothesis as a statistic. And my null hypothesis is that the points from some delta will drop into that epsilon with the probability of a coin flip, 50-50, which isn't very high. It could be 0.3, it could be 0.6. It doesn't much matter, as long as you don't go to extremes where you're always proving something or never proving something. So it works pretty well. Turns out with 0.5 of a coin flip, you can reject that null hypothesis as long as you get 6 points mapping into that epsilon. And that'll reject it at a level of 0.98. Now, the question then is, how small can you make that epsilon and still reject the null hypothesis? And of course, it's finite data. You can't go to 0. You can't take the limit. But I'll see how small you can go. And the smallest you can go, I'm going to call epsilon star. And we'll use as our statistic, how big is that compared to the minimum possible epsilon? Finite set of data, so there's going to be some average distance below which points don't have a neighbor. Or how big is it compared to the size of the attractor as a whole, standard deviation? You can use either of those as a continuity statistic. I'm going to do this. I'll show you how this works. Remember, they depend on the amount of data, and you can't go to 0. So more data will probably shrink this epsilon minimum. This should shrink too if there's a continuous function. If it doesn't, then we could say we have a problem. There's something discontinuous there. So let's try that. By the way, this was first published in 1995. A simpler version of this. This is a much more sophisticated with the null hypothesis and so on. We published a few other things, and recently, in fact, this was used by Kurtz and Kish and Marwan to talk about how you could use this kind of a statistic to help you gauge when you're trying to do an embedding with data. And that's a nice paper, by the way. So they use this to continuity statistic too. So you could do a differentiability statistic. I'm not going to get into it. You could look at the local singular value decomposition and see how many singular values you have. Does that match the dimension of the attractor or so on? It's a tangent space idea. I'm not going to emphasize that. I want to stick with the continuity statistic more than anything. I think this is a good way to have a statistic, but I know people don't think of continuity as a statistic. But it assumes nothing about the functionality. I'm not assuming it's a linear fit or polynomial fit or Fourier transform. It doesn't matter. We assume nothing about it. We're just looking to see if there's a function. It's for one direction only. If you want to look at the reservoir back to the drive system, then that's a different statistic. They're independent. It could be a non-invertible. It's local, which is what you want. It's dependent on the number of points in the system, which makes sense for a statistic. And this relationship to the size of the attractor, that's about the relative size of the smallest discontinuity that you can say you don't have if you can reject the null. You can't say anything about smaller discontinuity. So it's pretty clear as to what it's telling you. It should scale with the minimum, which I mentioned, and it's evidence, not a proof. It depends on the points. Yes, of course.
Yeah, so the size is one very small feature of the number of points.
Well, I mean that it's dependent on the number of points. That's, am I saying what you?
The number of points. It seems to me a stronger statement to say it depends on the point.
Oh, okay. Well, I thought I said that. Sorry, maybe I'm not. Depends on the number of points. Are we agreed? Okay. All right. Maybe we need another coffee and talk it over. Okay. So let's try this out. Go back to this one here, this situation, where we have a Lorentz driving a polynomial reservoir. And in the polynomial reservoir, there's a damping factor, kappa. And I'm going to set that at a value and let this run, gather the data, and take a look at the continuity statistic for this system, which does seem to give pretty good y and z values. So when I do that, I look at the continuity between, for the possible function driving from the drive to the reservoir. And when I do that, if I plot it against the standard deviation, I get something that falls as the number of points increase in my data set. Makes sense, because you can go to smaller and smaller epsilons, and there'll still be points. There's enough density of points to have that. Or I can look at it with respect to the minimum epsilon, the smallest one you can get, and that stays pretty constant. So this statistic is saying, as long as you keep adding points, it looks like, in fact, you can go to smaller and smaller epsilons. That says that there's a likelihood that there's to this epsilon size, there's a continuous function from the drive to the reservoir. How about the other way around? The other way around, reservoir to drive, we get the same thing in this situation. And which is good because we are able to reproduce the y and z out of this system. And this strongly suggests that there's evidence for a continuous function back and an inverse back onto the drive system. So you add I'm not going to go into it, but you can add an analysis of the singular values, and it looks like there's a differentiable also function. So we would say, it looks like we have a homeomorphism, maybe a diffeomorphism, just from the data. Okay? So for people who are in mathematics, that may seem a little odd to combine those words with statistics, but if you set it up right, I think it works pretty well. This is an interesting situation. Now we can do this with this same system, and let's vary the damping, because there's this whole idea, which Tom kind of really checked out first, about needing to be at the edge of chaos for these systems to work. And let's take a look at that. Let's vary the damping. Well, when you do that, this is the training error now. So this is like the error on the z component being trained when the x component drives the reservoir computer. As I vary the damping, and the damping is increasing in this direction, toward the left. So if I have a very high damping, I don't get great values. I get close to 10% error for the z component reconstruction. But if I pull the damping down, I come down to a pretty low spot right here where kappa equals 1, where I get fairly good reconstruction of the z component by a little over more an order of magnitude, better than when you had a lot of damping. But if you go to the edge of what they would call the edge of chaos, because this system goes unstable at a kappa about 0.2 here, 0.9, sorry, 0.8. What happens? Does it get better and better? Well, no, you can see that now the training error goes up. So being at the edge of chaos looks like things aren't working. And so let's check this with the continuity statistic. And we take a look at the continuity in both directions as we vary kappa, the damping. And you can see if we go from make sure I get the colors right here. If we go from the reservoir, look at possible functionality from the reservoir to the drive, that's the blue line. This is actually the size of the epsilon versus the standard deviation, so that the continuity statistic gets very good. It's best here at kappa equals 1. Well, that's where the training error was good. And then it gets worse. In fact, if you get even closer, it gets terrible. If you look at the continuity of the system as a possible function from the drive to the polynomial reservoir, it starts very badly near the instability, but then gets better and better as you go out. So one of the things you notice that I've had people say, well, you just want to damp a lot. Well, you don't want that either, because that really squeezes all the data down into a very, not data, but the systems down to a very small space. And you don't want it near the edge of chaos, because you're not going to get good continuity there. The sweet spot is somewhere in here, and that's certainly where the testing error is the best. So I would say that this continuity is telling you you're moving away. As you move away from kappa equals 1 in either direction, you're moving away from a embedding. You're moving away from a continuous and invertibly continuous function from the drive to the reservoir and back. And you're not getting any kind of a good embedding as you get away from that. So that connects it to something that's important, namely the testing errors. Let me see where I want to go with this. Oh yeah, so this actually is vaguely related to what Professor Ortega talked about, and that's this idea of fading memory. And you can see here that you do need some memory, and I'm going to emphasize that now, but you don't need too much, and you don't want too little. The testing I showed you just a minute ago should be saying that, but we'll talk a little bit more about that here. So if we look at, go back here. So if we operate up in this area where the training error and the continuity statistics are best, we say we get good continuity, and in fact we do get good errors or low errors when we train on the data. If we look at where there's a lot of damping, we actually found that continuity statistic goes down, but that means there's large dissipation going into the reservoir. The reservoir has a lot of dissipation, and you're losing information. And so you're not going to get a good statistic going back. The reservoir computers are squeezed down to a small region. And what does that mean in terms of, come back to Dawkins' theorem. What that means is the damping is too high in this, which means you're mostly only looking at back in time, points very recent in time. You're not looking back at points before that. So in terms of, if you want to think in terms of Dawkins' theorem, you're throwing away some dimensionality here. You're just not counting those points back in time, when you really should be, because it's a high enough dimensional system that you want to have those involved in the reconstruction. So the reservoir is not going to do good reconstruction if the damping is too high. You could think of it as under-embedding. If the damping is low, where you're near the edge of chaos, as people like to say, there's small dissipation, the nearby Lorentz points spread out more, and the inverse is highly contractive. So what that means is you're looking way back in time, and that can give you a lot of problems when you try to reconstruct an attractor. There's a well-known theorem, not theorem, it's a conjecture, Kaplan-York conjecture, where if you take too many components to try to reconstruct something, you'll actually end up with, by raising the dimension of the system itself. And that's basically what's happening, is the reservoir is raising the dimension. You're looking so far back in time that if the system's chaotic, all the stretching and folding ends up adding much more complexity to your reconstruction. And there's actually a formula for that. It's Kaplan-York formula. I think it's just a conjecture. I don't think that's ever been proven. But a lot of the numerical tests with that certainly show that it is an over-embedding, and you're really ruining your reconstruction. Of course, that reconstruction is happening in the reservoir, so it's giving you bad values for your reconstruction of the Y and the Z. So I don't know, how many minutes? 2? Okay. You can use this to predict, and what I like to say is post-dict. People don't use that word very much. How well you would do if you try to predict the system or even look back in time. This is the training error for predicting into the future or post-dicting into the past. This is the continuity statistic for doing the same. And the continuity statistic tells you, well, you have very good continuity here. You have probably a function going back and forth. It's one-to-one. Here you're starting to lose that. You go back into the past, you're starting to lose that. And that's certainly what happens with the training here too. This, I think, is the idea of fading memory also, where it's, but you could, what happens here is you're actually quantifying it with real data. So you can use this to talk about fading memory, not just as a rough concept or a vague concept, but you can actually talk about how much you have, don't have, or how you should adjust the reservoir computer, which if you're building them, makes sense. So I have a whole other part about detecting the basins of attraction. Professor Ortega mentioned some things about this, and there are cases where you get the reservoir possibly dropping into one or another attractor, depending on the initial conditions. It happens, and you want to be able to know when that happens. And if you have several hundred nodes, looking at the data doesn't tell you. So I have a statistic for that. It's very simple. If you are familiar with the distance between two sets of points in a metric space, it works very similar to that, except in a statistical basis. If somebody wants to see that, I'd be glad to talk to them about it. It's pretty simple, but it came up in some of this work because we got terrible values at some point and found out that we actually had two basins of attraction. We had two different attractors, and it was subtle because the reservoir computers were almost exactly the same from the two different systems, started in a slightly different place, the Lorenz systems, except for two components of the reservoir. So if you had several hundred components, you don't want to have to look through all of them. This will very easily, it's a very simple statistic, but it'll easily sort that out for you and tell you you're really on another attractor. So I'm not going to go through that. I will skip fast through it and go to the there we go. Let me get rid of this. And I'm using Dynamics to do that, but there we go. So we have a paper, so hopefully soon go up to the archive as soon as I write it. So even in simple RC systems, nonlinear phenomena are important, and the analysis that we did captures the behavior more quantitatively, I think. I think some of it's coming out now, as Professor Ortega's talk would also show, that the AI communities have taken the dynamics to an interesting and potentially useful direction. I have a whole spiel I can give you on how the nonlinear dynamics people should have invented reservoir computers. Came that close, but didn't. But it's actually Moss and Jaeger who did in the early 2000s. But I think it should be informed by nonlinear dynamics now. The point being, we also that for these statistics, we don't always have accurate models. If you're building these things, you don't know about all the dynamics. Everything isn't always contractive. If you're looking at neurons and networks of neurons, you might not have a clue what the dynamics are. Sigmoids aren't neuron dynamics. I know they're called neurons in the neural network world, but they're really not. If you look at neuron dynamics, they're much more complicated and much less controllable in a way. And I make a point here, it's just a little bit independently, but I think you have to be careful. You cannot measure reservoir properties independent of the drive signals. And this is, people in nonlinear dynamics know this, but I've seen people say, well, we'll just drive it with noise and then see what the damping is. Well, what you drive with will also determine the dynamics of the reservoir. And there's a very simple example to show that from nonlinear dynamics without even needing a reservoir. So just be aware of that. The drive matters for the properties of the reservoir dynamics. And I'll stop there, take any other questions. Thanks.